This is our last day working on these cross-section volumes, and so we're going to kind of review as we go. Square is one of the most common ones that you're going to get, and so the area that goes inside your integral is just the area of a square, so that's just going to be s times s. So that's an easy one. Next one we're going to look at is going to be a rectangle. So the rectangle is basically just going to be your length times your width, and for our example, the length is just going to be your s. And the S is always that part that touches the shaded region that we call your base. And then the width could really be anything, but it's usually a multiple of your S. Okay, the next one we're looking at is semicircles. Remember, for a semicircle, what we really need is the radius. The radius is going to be half of your S. So we always write that down. The area of a full circle is going to be pi r squared. We have a semicircle, so we're just doing half of that. We're going to replace the r with 1/2 s, and then after you square it, you're going to get 1/4 s squared, and there's still a pi over 2 in front of it. So that's how we're getting a pi over 8 in front of our s squared. So the area of one slice for a semicircle is going to be pi over 8 s squared. Again, this is just review. Let's not forget our triangles. The first one is an isosceles right triangle. Looks something like this. Both of the legs are the same length, and it has a right angle in the corner there. So basically that's just going to be half of a square. If I cut the square in half, you see I'm going to get two congruent pieces here. So this triangle is really just half of the square. So we know the area of a square is s squared, and we're just going to put a 1/2 in front of it. So if one of the legs touches the base, then you're just going to have 1/2 s squared. If the hypotenuse touches the base, then I think you could see we're ending up with 1/4 of a square, because we can fit about 4 of these in a square. About 4 of these little triangles in a square. So when the hypotenuse touches the base, and again, this is going to be another isosceles right triangle. It's going to look something like this. In that case, you just get 1/4 of the area of a square. So 1/4 s squared. And this is our new one today that we've never done. This is an equilateral triangle, so all 3 sides are going to be congruent. And of course, all 3 angles will also be congruent. The area of this one is going to be √3/4 times s squared. So that's one of those things that it does take a little bit of calculation to figure out. So it's good just to remember that one. We are going to take a look at the calculation for this today. And we're also going to take a look at the calculation for this one, even though this is kind of an easy one. It's just 1/4 of a square. So let's have a look. So here's the first one that's just 1/4 of a square. Again, it's an isosceles right triangle. So that means both legs are going to be congruent. But in this case, it's the hypotenuse that's touching the base. So if we were to have a square, I think you could easily see that this is really just going to be 1/4 of a square. If we do the diagonals for the square, you can see that's just 1/4 of a square. So it's pretty easy to see intuitively. But let's actually calculate it. If you remember the rule for a 45, 45, 90 triangle, the rule is that you're going to have x, x, and then the hypotenuse is x√2. The only thing we know about our triangle is that the hypotenuse is our s. That's the only thing we know about our triangle. So we're going to match it up. We're going to say, well, s is going to equal x√2, and then we'll solve it. If s is equal to x√2, if you divide both sides by √2, you're going to get that x is equal to s/√2. So this x is going to equal s/√2. And so both sides are going to be s/√2. So we get this picture right here, and if you turn it sideways, it's pretty easy to see that the area of that triangle is just 1/2, and then the base times the height. Well, the base and the height are both going to be s/√2. So we can simplify that. √2 times √2 is just going to be 2. So you just have a 2 here. And then s times s is s squared. So we're almost done here. We have 2 times 2 on the bottom gives you a 4. So we do get 1/4 s squared for the area of one cross section. So that's the proof of it. But remember, this is kind of the easy one. Just think of it as 1/4 of a square. And that's the easiest way to figure it out and remember it. All right, let's look at one more example here. This is the new one. This is the equilateral triangle. So again, all 3 sides are going to be congruent. And of course, that means all 3 angles are going to be congruent. So what would be the area of this one? This one's pretty tricky. Remember, almost everything is a number times s squared. So in this case, the number is √3/4. And I just try to memorize that. There's a couple of tough ones. the semicircle, which is pi over 8 times s squared. That's another one that I just try to memorize. That's the semicircle one. So let's have a look. Let's figure out where we got this from. This is the new one that we haven't done yet. So we're going to start off with our equilateral triangle, which means all three sides are s, and all three angles are going to be 60 degrees. So we're just going to do half of our triangle at first. So this part right here is just 1/2 of s. We still have our 60-degree angle here, but the angle up here got cut in half. So instead of being 60 degrees up top, it's only going to be 30 degrees up top. So now we have a 30, 60, 90 right triangle. And we know the rule for that. Opposite of the 30 is going to be x. The hypotenuse is 2x. And then opposite of the 60 is going to be x root 3. That's the rule for a 30, 60, 90 triangle. And now we just want to match up what we have. We have 1/2 s, and that's going to match up with our x. So the hypotenuse is going to be 2 times that. So 2 times that would just give us s. And then the h, which is the thing we're trying to figure out, is going to be s over 2 times root 3. So that's the hard part. The h is going to be s over 2 times the root 3. So that's the big thing we were trying to figure out the whole time. Once you know the height, you're basically done, because the area of a triangle is just going to be 1/2 the base times the height. And we know what the base is. The base is just going to be s. So this whole time, really, we were just trying to find the height. We found the height. It's s root 3 over 2. So we can replace the height with s root 3 over 2. The base of this triangle is just s. So the base just gets replaced with s. We're basically done. We have our s squared right here. So the area is going to be s squared times, and then we have a 1/2 and a root 3 over 2. So that's going to give us root 3 over 4. Now you don't want to do this calculation every time you get this kind of a cross section. So the best thing to do is just try to remember this. It's not very likely that you would get this kind of a question on the AP test. They usually give you squares or something real simple. This is more of an advanced one, but you never know. Now, this is just a review again. If you want to do the cross-section volume, basically what you do is you just put the area of one cross-section inside your integral. And then, of course, your integral goes from A, so that would be the starting value, all the way to B, so that would be your ending value. And that's pretty much it. So if you can just figure out what is the area of just one slice, you're almost done. Okay, now we're going to look at a few examples. For this example, we're doing rectangles, and the height of each rectangle is going to be 5y. So they just tell you exactly what that is. Telling you that the height is 5y. I put a w, which kind of means the width, but you could call it the width or the height. It's basically the same thing. The other side of our rectangle is just going to be s. And so let's look at what s is. Here's the s over here. In this case, it's going to be the right minus the left. And that's because the cross sections are perpendicular to the y-axis. So we're drawing our s's perpendicular to the y-axis. So if I do the right minus the left, my s is going to be the right, which is 7 minus y, and then minus the left. And the left is 2 times the third root of y. And that's pretty much it. Our rectangle is going to be just the s times the 5y. And that's pretty much it. We do have to find the value of k, which is a y value. We are going from 0 up to k. So those are our bounds. But what is k? Well, to get k, you just solve where this function is equal to this function. And you're solving it for y. So k is actually a y value. Now, if you store this number in your calculator, you can just do 0 to k for your bounds, and then you'll get your final answer of 64.721. For our second example, we're going to do the exact same functions, but this time our cross sections are going to be perpendicular to the x-axis, so our s's are going to go up and down. We actually need two different s's. We're going to have to find the volume of the green one separately, and then the volume of the purple one separately. So the cross sections are squares, so that part's pretty easy. The problem is we can't say that s is going to be the top minus the bottom when we have two different tops, right? Over here the top is x to the third over 8, and over here the top is 7 minus x. So we're going to do this with two separate integrals, one integral for the green and one integral for the purple. Okay, because they're squares, the area is just going to be s squared. So for both of them, the area is s squared. But for the green region, the s is going to be top minus bottom, where the top is f. So the top is going to be x to the third over 8. The bottom is 0 for both of them, so that's not really a big deal. You don't have to put minus 0. but our S1 is going to be x to the third over 8. So that's what's going to go in our first integral. For our second integral, we're doing top minus bottom, but the top is g. So the top is going to be 7 minus x. And then we do minus the bottom, but that's just minus 0. You don't have to worry about that. So our S2 is actually just going to be our g function, which is 7 minus x. Now we do have to solve for the k because our first integral goes from 0 to k, and our second integral goes from k to 7. So we got to find out what that k is. That k is an x value, so we're just going to set this equal to this, and that'll give us our x value that we're calling k. Turns out that we get 3.137. So we just have to solve where these two equations are equal to each other, and of course we're solving for x. Don't forget to store this value for k in your graphing calculator, and then you can just type in the integral from 0 to k. And for the second integral, you can just type in the integral from k to 7. It's much easier than typing in the entire decimal. So we got to plug in both integrals into our calculator. We're actually adding two integrals together, and our final answer should be 25.888. For our next example, I want to remind you about the equation of a circle. If your circle is centered at the origin, the equation is going to be x squared plus y squared equals r squared, where r is the radius. Now in this example, we're using the letter a for the radius, but it's basically the same thing. If you solve this equation for y, you got to start by subtracting x squared from both sides. So you get a minus x squared over here. Then you're going to do the square root on both sides. So here's your square roots. And the square root of y squared is the same thing as the absolute value of y. You can get rid of the absolute values if you put a plus or minus. And of course, you can move the plus or minus over to the other side. I'm writing it as minus plus. So what that means is that you get y equals the negative 1. The negative 1 is going to be the bottom. And y is also equal to the positive 1. And the positive 1 is basically going to be the top. So when we write it like this is an equation. It's not a function, but it's an equation. That's the entire circle. If you solve it for y, you get two pieces. You get the top, which is the positive. So here's your top. Now this is actually a function. Then you also get the bottom, which is the same thing, but with a negative in front of it. And that's the bottom half of that circle. Now we're going to keep this in mind, and we're going to do our next example. So for this example, the cross sections are going to be equilateral triangles. So I have an equilateral triangle drawn here just to remind us. The area of an equilateral triangle is going to be root 3 over 4 times s squared. For this example, the base is basically going to be this entire circle. So the base of our region is this entire circle. Now we're not actually using numbers for the radius. We're just using a letter A. So this is more of a conceptual example, but you often would see something like this on the real AP test. They really like to test your understanding of the concepts. So they do sometimes put questions like this in there. So our radius is just the letter A. So the top half of the circle is going to be square root of a squared minus x squared. And the bottom half is going to be the exact same thing, but with a negative in the front of it. So our s is going to be the top minus the bottom. And so here's the top. So I'm writing that right here for my s. And then minus the bottom. So we're subtracting the bottom. The bottom has a negative in front of it. So we're ending up with a minus and a negative. So minus and negative is really plus. So you get this one plus this one, and it's the same thing. It's the same piece. So really we just have two of those things. So that's going to be our s. So our s is two of these things, and we take the area of one cross section for an equilateral triangle, plug it in right here. We just solved for our s, so we can plug in our s. And of course, we're perpendicular to the x-axis. That's the reason our s is going up and down. So we're going to go from negative a all the way to positive a. So those are going to be our bounds from negative a to positive a. You can actually solve this with a graphing calculator, or you can solve it on your own. Now, what if we used a number instead of just a? What if we use an actual radius? So for this one, we're going to use a radius of 4. So if our a was 4, all you have to do is put the 4 for the a everywhere. So if we just go everywhere and replace all the a's with 4s, we're going to replace all the a's with 4s, then our final answer, instead of having an a to the third, it's going to have a 4 to the third, and it's next to this 4, so now it's 4 to the fourth. Well, 4 to the fourth is 256. So that's how that would be different if you actually had a number for the radius instead of just the letter A. Number 5, this is our last example. For this example, it's just a basic one. We have squares for the cross section, and they're perpendicular to the x-axis. So each square is going to be perpendicular to the x-axis. Now our top function is just cosine, our bottom function is just sine. So that's our s, just going to be cosine minus sine. So that's a pretty easy one. A lot of us even know where they intersect. We know that sine of 45 degrees and cosine of 45 degrees both give us root 2 over 2. So that's where sine and cosine are equal at 45 degrees, or in this case, we're writing it as pi over 4. So our integral is going to go from 0 to pi over 4. And of course, the area for a square is just going to be s squared. We already did our s. So this is actually a pretty easy one. We can write our final answer as pi over 4 minus 1/2. Or you could also write it as a decimal. It's up to you. I prefer to write it as the exact answer as long as it comes out nice. This one wasn't too bad.